Epiphany, my multi-sensor fusion and vehicle-to-vehicle collaboration in autonomous vehicles, a comprehensive framework for self-driving paper. So a little bit of background. Right now, the current commercial industry baseline or standard is Tesla with their FSD or full self-driving mode. So Teslas are able to autonomously navigate through lanes with lane lines. They're able to change lanes. They're able to recognize traffic signs, most traffic signs. They're able to recognize stoplights, and they also have some additional features like Smart Summon, which is the idea where on your app you can summon your car to actually come and drive around the parking lot, find where you are, and pick you up, which is pretty cool. Now, Tesla, they also have that. Now, there's been some like accidents related to that. The autonomously summoning car, there's been issues with the car running into things, not seeing signs, hitting something, and then worst of all, it doesn't stop. It will hit something and then it does not stop. It doesn't realize it hit something and it will keep running into things. So it also, at some point, it has some issues identifying or distinguishing between different levels of brightness in the sky and different signs. And another thing with Tesla, so Tesla now they have transitioned to, after a couple years ago, they were using ultrasonic distance sensors, but now they've transitioned to a fully camera-based approach for autonomous driving. And they claim, of course, none of their code is publicly available, but they claim to be using a CNN neural network machine-based approach. So Waymo is another kind of one of the probably best autonomous driving systems. They use LiDAR sensors and they use camera data. Now, some of their drawbacks are their services are only in use in San Francisco and some other cities as part of Waymo One. These are completely driverless, autonomous taxi services. And they have it so that they have an app, people are able to request a taxi, kind of like an Uber, and it can go and pick them up. Now, these cars are expensive. They have lots of equipment. They have massive LiDAR sensors. They have massive compute clusters inside of the cars. They have servers. They have computers. They have a lot of equipment, and this isn't really lightweight or practical for everyday people. Now, OpenPilot is what we use as a benchmark for this project, and this is a open source self-driving model. So how this works is it's a repository that's available online. You're able to clone it, and then it supports various different cars, and then you can also, if your car's not supported, you can add it. And this essentially works by plugging in either your computer, or you can plug in their device that they sell, which is referred to as the Comma. I think it used to be called the Comma One. Now I think it's called the Comma, which is essentially a lightweight Unix-based computing device that you plug into your car. You plug it into your car's OBD2 port, which is the port manufacturers and automotive engineers use for car diagnostics, and it communicates from that computer to your car's ECU, your ECU from your motors, and it manually sends signals based off either your car, if your car has some newer cars have front-facing cameras to see traffic signs. So you can connect it to your car's front-facing camera, or you can provide an external webcam and connect it from there. And then based off of that camera footage, it will send signals manually to your car to overwrite your motors. So this works, essentially, this is very crude level 2. It's essentially very mature level of lane assist, where it is able to detect lane lines, and then the main benefit is, even though some car automotive companies, they have a form of lane assist, it requires you to have your hand on the wheel at all times, and you can't take your foot off the brake, or at least some newer cars, they yell at you when you try to take your hand off the wheel. For OpenPilot, since it completely overrides those signals, it will not give you a warning to do not take your hand off the wheel. It will not tell you need to stop. It will completely overwrite any of your vehicle's default signals. Now, so we kind of started as a baseline to utilize their Super Combo model. And we use Yaboom's robotic vehicle for research and testing purposes. It's equipped with an NVIDIA Jetson Nano board and an expansion board, which the motors and various different like USB devices are able to plug into. So that's where our camera connects, and that's where our LiDAR connects. And we have this equipped with a LiDAR sensor and camera. Now, motivation. For our autonomous semi-driving framework, the first thing we want to focus on is lane detection. Now, some newer cars now have some form of lane assist where they try to stay in the lane. And so that is kind of a good starting point where we want to make it so that we are able to detect and then fully autonomously stay in the lanes and then even turn in the lanes, which at some point is a challenge. Now, we also want to additionally work on implementing vehicle detection and tracking. So if there is a vehicle in front of us, we want to recognize that there's a vehicle in front of us. We want to be able to either use LiDAR data or we want to use camera data to establish that there is a car in front of us and to stop or to continue moving. Now, we also want to do something like Tesla, where they have traffic sign detection and where they have light detection. Now, we also additionally want to have our robot if there's another robot, we want to have them communicate with each other and we want to have them send signals between each other so that we can stop potential collisions from occurring. And to add a form of explainability, we want to look into 3D virtualization to take in our robot's data from our LiDAR sensor and from our camera data to actually visualize objects in 3D so that we can create a sense of surrounding around the robot. Cool. All right. So this is the map that we use for our robot. It is rather large, so we are only focusing on using that half right there. And then these are some of the various different signs that we're using. And then that is a stoplight that we will go into as well for some of our demo videos here. Now, this is the robot used. As I mentioned, this robot is the X3 from Yaboom. And so as you can tell right here, I have the wheels labeled. That's because the left and right wheels and the back and front wheels, their curvature of the wheels is differently. So at first when I put this together, I put one of the wheels on wrong and it just kind of moved around in a circle. So that's a little bit important. At the top of this vehicle right here, we have the camera, and this camera has a little bit of depth perception. So this is good for seeing objects that are in front of it. Or at least this is good for performing object recognition for objects that aren't exactly right in front of the robot. And then right underneath of it, we have our LiDAR sensor, which is used for getting that amount of distance. And then right here, this weird thing behind it is a screen that is on the robot for displaying. Again, for our experiment and framework overview, we're going to break this down into going through each one of these components. Now, so the first thing we implemented is lane detection. And since we are using a CNN model for our lane detection, we need data to train that model. In order to collect data, I essentially took video footage of the robot going around the track correctly. I manually programmed it with speed and turn values to go around correctly. And then I took these videos and I segmented them into frames. And then past the frame video, there was a CSV file associated with these frames that had speed and turn value. And then we passed these values into the model where it was able to predict movement. Now, we looked into using EfficientNet CNN. This is what SuperCombo, the OpenPilot, uses as their backbone, and they use this plus some additional layers. Now, we also implemented long short-term memory, or LSTM, and the benefit of this is we are able to get a sequence of predictions across multiple frames. So we can look at previous behavior, and this is really important, previous frame behavior. This is really important when we're looking at something like turning, because due to when we see our robot turning, every frame, it's not able to perfectly capture the fact that we have two identical lane lines inside of that. There's going to be some frames where it's not going to have a perfect picture of the lane lines. So we want to know what the behaviors leading up to those frames where we don't have data look like. So then we are able to generalize better on those frames. Now we take our trained model, and that is saved to the robot, and we use that trained model to perform real-time inference on live coming in data from the robot's camera. Now, here is a video of our lane detection. As you can see, the robot is going pretty well. It slows down a little bit for the turns, but it's still able to go around. It just slows down a little bit, and then it's going to pick up speed back here again for just seeing the lines right there. And as you can see, in the scenarios where it gets kind of close to one of the yellow lines, it's because it's seeing at least one of those lines. So it's trying to kind of predict where the parallel line would be. And so it's not exactly sure where the center is when it does that. And here we go. Here's the robot going in the opposite direction. As you can tell from this, I'm not using the white lines on the road because I feel like that's not a accurate predictor of real life driving. That's not like there's not white arrows on the road telling you which direction to drive in. That doesn't really make sense. And there we go. As we can see, it made another lap around. Cool. Okay. Now, another feature that we look into implementing is the vehicle detection and tracking. We want to be able to use a LiDAR sensor for distance calculations to get the amount of distance that would be in between one robot versus another robot, so that way we can maintain a safe following distance. And we also want the robot to be able to use the camera to identify and then follow the other robot or vehicle. This is important because we want to know if it's going to mimic driving behavior. We want to make sure it's mimicking a vehicle's driving behavior, not that it sees something like a traffic sign and it says, okay, let's follow the traffic sign. No, we want it to see a vehicle and say, follow the vehicle. And here's a little bit of a demo for that. As you can tell, the vehicle in the front's moving, the vehicle in the back's moving, and there's a set distance between the two that stays pretty consistent. So for traffic sign detection, we implement this using You Only Look Once, or YOLO model, which is a lightweight model that is able to perform classification based off of one neural network pass. And we use the various traffic signs that were included in the map picture, and we use the traffic light there. For our training images, we augment these images with performing rotations, translations, we change color, we change contrast, and some of these images have different objects in them, or they have different things in the background that the model needs to distinguish between to just get the traffic sign. There's some of them, as we will show later, that have part of the image covered up, and it still is able to classify. The robot will check if an object is detected using LiDAR, so it will know that there's something in front of it, and then if there's something in front of it, go ahead and perform a call to the model. These are various different types of the traffic signs. So as you can see, there's speed limit 30, not 30, 1 and 2, which I believe is used for just telling it go like route 1, route 2, or something related to parking. And then there's the horn. And then as you can see down here, there's a sign that says right. And as you can look from this picture, part of the sign, almost all of the sign is covered, and it still knows that it's because for the right and left arrow signs, the arrows look differently. So it's able to say, okay, it knows with like an 80% confidence that this is a right sign. And here's a traffic sign demo. There's a stop sign. As you can tell, it's going to go forward. It's going to see that sign. It's going to stop. This is the red light. It knows that this is a red light, so it's not going to go forward. Versus this is a green light. It sees a green light, so it goes ahead and it knows it's good to go forward, and then it stops before actually reaching the light. So we also want to look into implementing vehicle-to-vehicle collaboration, where we have one vehicle and we're going to be able to communicate signals between these two vehicles so we can stop something like a collision occurring. These vehicles use data distributed services, or DDS, which is actually built on top of the ROS protocol, which the vehicle is already using ROS to send signals between the motors, the camera, and that NVIDIA board for processing. Robot 1 is going to go ahead and create a publisher, and this robot is going to have a domain ID of 0. Robot 2 is going to create a subscriber, which is going to have a domain ID of 1. Robot 1 is going to go ahead and it's going to go out and it's going to publish its position and velocity data. Robot 2 is going to receive that position and velocity data, and then it's going to be able to communicate with the other robot. Here's an example here of this happening. So as you can tell, these robots, they look like they're about to collide. Okay, see, now both they stop, and then the first robot goes forward a little bit. Now this is an example of this robot going to park, and it is going to turn into here based off of knowing this robot's position and based off of knowing that there's a traffic sign right there. So this robot, it's been assigned to park. It knows that it needs to park. Now it needs to get in between both of these robots. So it's using its sensor and the robot's position data next to it to actually know a accurate position to go into. And then when it lines itself up in the parking space, it's looking to see that that parking sign is right in front of it. Based off of that, we want to use 3D virtualization as an explainability for what obstacles are actually around the robot. This is more of a benefit to the user or somebody who is sitting in a car so that they can see the 3D view of what is around the car and what the car thinks is an obstacle. We are going to be using LiDAR sensor and camera data, and we are going to display these obstacles in RViz. RViz is a robotics, it's a 3D visualization platform that is built on top of ROS as a robotics platform for performing visualizations and simulations. We're using octomapping, and octomapping uses octrees for 3D mapping. And then octrees are just tree-like structures, and they recursively divide 3D spaces into smaller 3D blocks. We have a node that's going to subscribe to the 3D generated camera from a TF transformer between the camera and the map frame. And then so the camera and the map frame are going to be communicating between data. Here's an example right here. As you can see, this is actually the blocks that are being displayed in the back. That's the wall that the robot's seeing when it's going forward. And then as it's going to go ahead and turn, that's going to be the wall that's going to see that way. And then one of the little blocks that it gets in front of it is going to be it's going to be the stoplight that it sees in front of the wall. Some results for traffic sign detection these are just an example of some of the classes that we used. As you saw in the previous picture, we have the not 30, which is just the 30 sign with the line drawn across from it. And then there's the 30 as well. I thought it was pretty interesting that it actually is able to distinguish between the instance of not 30 and 30. Kind of the same with the right and left arrows. I thought it was interesting that it actually was able to tell that the arrows were drawn, the right and left were drawn slightly different to the point where it could distinguish between the two of them. And then 2 and 1 just kind of showing you can read numbers. And then there's alarm sign, which sort of looks different from the other one, so it makes sense that it's able to classify that correctly. Now, we look at our having a mean accuracy precision of 94% across these various traffic signs, which seems to be pretty good. For lane detection, we focus on doing classification here. Now, our best test accuracy was reached at epoch 20, and that was around 92%. Now, to ensure that overfitting is not occurring, we basically have, for both this and YOLO, there's early stopping if there's actually no improvements with the model. Some of the challenges that we ran into here was my first attempt for doing lane detection. A common approach online is just using OpenCV to get the contrast differences between the white lanes for the robot to stay into, and then the black or gray road. And the issue with this is there's a lot of other things on the road. In practice, this doesn't really work. There's a lot of other components, and like for our case, there's actually the arrows on the road. So, an interesting thing here is that when Tesla was first creating their self-driving system, they were fully basically using just OpenCV for their lane detection, and they were just relying on colors, or they were just kind of relying on clearly seeing lane lines. So there was one point when I think they were first getting ready to ship their software where there was one point. It was, I think Elon was trying to get the car to drive from like the factory to his house, and there was one turn in the road where the lane lines were really unclear and the car wasn't able to turn. So then Tesla actually went probably not Elon Musk himself, but he had people do it, and they actually went in and they repainted the wave lines. And then he was like, "Oh yeah, it works now." So that's one solution. That's not the solution we took. We turned to using machine learning models for that. Stemming from that problem, I looked into using, or I did some work with using OpenPilot Super Combo model. Their model is it just uses a EfficientNet. It uses the mobile version of EfficientNet as that backbone, and then it also has some additional layers on top of that. One of their problems is even when I train this with my own data, um, one of their things was, incidentally, one of their very important image features was camera position, camera location. And a car's camera is going to be completely different from based off of where a robotic vehicle's camera position is going to be. And their model also got very confused by the fact that we had white arrows on the lane. It thought that it was a lane line, and it thought that kind of any additional markings was a line in the lane. And looking at the output between some of their convolutional layers, it got really confused on seeing other stuff, and it just, if it saw anything on the map, or if it saw anything on the map that kind of looked like a lane line, it just automatically assumed that it was a line. And so there was one part where it goes to turn, and it doesn't understand that the robot needs to turn. It doesn't understand where the lane line is. It thinks the lane line's in the middle of the road. And then, so one of the issues is just having the robot being able to turn correctly. Using LSTM, where it's able to use a lot, able to compound the previous frames values to make a good trajectory position, to make a good trajectory prediction. Fix this a little bit. As you can see, it's still a little bit slow for some of the turn values just because it cannot see every single frame. If we had kind of maybe more feed, we're also working a little bit constrained here as we have only one camera for vision feed. If we maybe had side-facing cameras, we would probably be able to get better data feeds. So that would potentially solve that problem. Also, one of the problems is the robot wheels that we have. Sometimes they keep the robot, it will make a prediction, it will do the movement after prediction, but sometimes the wheels will turn for more rotations. The wheels will have to fully rotate, and then after they rotate to go to the amount of speed or the amount of time it's supposed to actually move, sometimes it will spin for additionally a little bit longer. So sometimes it just kind of it kind of yanks it, or will kind of drift it a little bit in the wrong position. And we also, something that we needed to do was optimize our code for running on a more lightweight device. Initially, we had very slow model predictions, very slow model classifications, where it was able to correctly classify, but it was taking forever to go in between the classification and the actually moving the robot. We fixed this problem by using a TensorRT, which is it's one of NVIDIA's API, basically NVIDIA's API, their package, their version of code acceleration that we looked into, and we created weights for using that. And this is actually kind of similar to Comma AI or OpenAI, OpenPilot's company. They have their own machine learning framework, which is called TinyGrad. So it's kind of similar to creating something. It's kind of similar to something like PyTorch, and they actually have optimizations for all of their code. So this is kind of similar to what they were doing. Okay. So as an overview, we went into lane detection, went into vehicle tracking, multi-robot communication, sign detection, and 3D virtualization. All right. Thank you for listening.